Okay, so we're back. Thanks for bearing with us. And indeed, 92 people answered. 89 people out of 92 picked 3 out of 6 for the probability of E1. We'll see if that's the right answer in a second. What I'm going to do here is on this little piece of paper, I'm going to just highlight these events. So this is your little sheet. Let me zoom in. I zoom in a bit. Woohoo. Woohoo. Okay, perfect. So E1 is the first dice is even. Let's try it in green. E1. First dice is even. And that's going to be either the rows or the columns here. So the first dice is the columns. This one, this one, this one. That's E1. And so I think the real answer is 18 out of 36. 3 groups of 6. 6 plus 6 plus 6 is 18. 18 out of 36. But of course that is equal to 3 out of 6. So everybody in the Mathematize got that right. So very, very good job there. So if you were amongst the people who selected 3 out of 6, you got it right. What about the next one? The probability of E1 given E2, and you have to know about this silly line thing, right? E1 given E2. And this time, again, 79 people think the answer is 3 out of 6. So it's like you got some new information, and all of you guys think that the probability didn't change. Let's go back to the .cam. Now let's do E2. E2 is the second dice is even. Okay, and E2 really are these rows narrow. That's E2. So now, when you condition on the event E2, when you do anything given E2, the answer is going to be something out of 18. Something out of 18. So I want to go up. Okay, there we go. So down here in the corner, when you condition on E2, it's like you delete everything except for these 3 rows in the middle. So the probability of anything given E2 is something out of 18. How many times were you there? And if you count up the number of things that are both in E1 and E2, there's this one, there's 1, 2, 3. Ooh, this pen is not working. Let's try this pen. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this time the answer was 9 out of 18. That's the probability of E1 given E2. You might notice 9 out of 18 is also 3 out of 6. So even though you guys picked 3 out of 6, that was a multiple choice, I made that the option. The real answer, I would say, is 9 out of 18. Of course, they're actually exactly equal. So everybody got that right as well. Very good. All right. What's the last blank? The probability of E3 given E2. And now, maybe, perhaps, is the thing. Let's see how many people got this one right. Oh, okay. So now it's a little bit more split. So out of 92 people who answered, we have either 1 out of 18, 1 out of 36, or 1 out of 3. And the correct answer, I believe, is 1 out of 18. So slightly less than half the people got it right. Let's do this one on the sheet of paper, on the .cam over here. So now we're doing the event E4, or E3, which is the sum is equal to 4. And this event is a little diagonal slice. We've done this one a bunch of times now. It's this little diagonal slice. There's E3, that the sum is equal to 4. There's 3 things in E3 originally. So the original probability was 3 out of 36. But if you're given E2, then you're only looking at these 3 red rows, right? And out of the 3 red rows, there's 18 total things. How many of the total things are in E3 and E2? Just 1. Just 2. So the probability of E2 given E3, E3 given E2 looks like this. It is 1 out of 18. The 1 being this guy, 2, and the 18 being these 3 rows. So out of the 3 rows, there's only one place, 2, that gives it to you. 1 out of 18. All right, let me think of why people got it wrong. I don't know. Most people, actually, 46% was the most common answer. So maybe people were closer than thought. Any questions or comments about that one? Again, you're going to practice some of these conditional probabilities on your homework due on Friday. Yeah?
Darn it, the homework
No, so in the homework, if it lets you put in a fraction, it counts all fractions as equal. Well, okay, any fractions that are equal, it counts as equal. So you do not have to simplify, and probabilities are really numbers. So 3 out of 6 is equal to 9 out of 18. Yeah. Any other questions? All right, I'm going to hand it over to Professor Humphrey, who's going to take it from there. And you'll see that this theme, two things that have the same probability, given each other, E1 and E1 given E2 are equal. That's going to be an important thing coming up soon.
So, oops. Get stuck there, we got that, we got to go to that. Which was the dead one, the green one?
The green one is dead, yeah.
Green one's dead.
Or wait, which was it? Yeah, the green one.
I think it was the green one, because you used the blue.
Oh, here's a black one.
Oh, that's not very thick though. Okay, today we're going to start into another example, something called earn problems. And before I do that, I just want to emphasize we're going to be attacking problems with a few different techniques that help you think about how to solve probabilities. We're going to be coming to something called Venn diagrams, and I also use a term Venn-like diagrams because there's certain diagrams that are very similar to Venn diagrams that technically aren't Venn diagrams, but that's a point for another discussion there. Tree diagrams or probability trees will be a technique we work with today, and probability trees are enormously helpful in helping sort certain types of problems. The thing with trees and Venn diagrams is they're sort of limited to what you can graphically display. And some of our problems get more complicated, and so we need to be able to think from relatively simple problems to more complicated problems. And one of the ways that allows us to do this is to use algebraic notation. And for some of the problems we have, we use counting rules, so-called counting rules. You may have known them as combinations and permutations are some of the most common counting rules that we use. Again, sometimes we think about the structure for simpler problems and then how we can extend those to more complicated problems. So we're going to work with paper, well, for me, paper. And we're going to consider a very simple problem, a couple simple problems involving urns and some balls in urns. And we're going to work these out with the aid of probability trees, and then we're going to do some interesting things with these probability trees. A key concept is going to be the idea of sampling without replacement versus with replacement. This will be something you've got to kind of keep an eye on and make sure you understand the difference between the two ways of sampling. And in the questions, a question that often comes up is, will a particular problem tell you whether it is involved, it's using without sampling or with sampling? No, not always. Sometimes we have to infer what the method of sampling is going to be. Again, we'll come up to examples of that where it may not tell you that you're sampling without replacement, but you should understand that you are sampling without replacement. And well, we'll have to ask this question. Doesn't matter if sampling is without or with replacement. So that's a question we'll try to address as we come into our questions here. And if the answer is yes, well, in some problems the answer is yes, and in some cases the answer is no. But if the answer is yes, why does it matter? So here's our very first question. So first of all, what is an urn? An urn is a bucket, okay? It's like a pail, a bucket, or whatever. And so you've got this urn, and it contains 5 balls. 3 are red, 2 are white, okay? And so if we're going to draw balls, I'll just use one dot camera for the one screen for the moment. Tis an urn, very elegant urn, and we've got 5 balls in that, and you know, I've got 5 balls, but I'll just say 3 are red, 2 are white. Okay. And we're going to reach into that urn and grab 2 balls without replacement. Okay, so what does it mean without replacement? It means that we reach in, we grab a ball at random, means that with equal probabilities, we're still using the equally likely rules. We're still using equally likely rules, but the equally likely part kind of keeps changing as we do some different things. So yes, they're equally likely, and we're going to grab one of those balls, and we're going to take it out of the urn. We're going to record the color. Okay, and then we're going to reach into the urn again and grab a ball at random, in other words, with equal probability of the balls that are in the urn, and take that out and record the color. Okay. Now I just said that we take the balls out one at a time. Some often ask the question, what would it differ if I reached in and grabbed both balls at the same time? That seems like a good question, right? Does it matter whether I take one out and then the other, or I grab both at the same time? It turns out it doesn't matter. Okay, it's equivalent to taking out one ball at a time. Anyhow, so let's take a look at running this experiment, and what I want to know is what are the probabilities that both of the balls drawn are red, both are white, and there's one of each color. Okay, so we're going to set this up as a probability tree. And this is our example 1. Two balls drawn at random without replacement. So we're going to reach in, grab our first ball, and so we're going to just call this our first ball, or first pull. And you can either get a red or a white ball. Okay, so I could either get a red ball or I could get a white ball. And then what I want to do is attach a probability to getting each of those colors of balls. And let's see, I'm off the screen. Okay, well, why don't I keep everything on the screen? That would be good. Okay. And let's attach probabilities now to each of those pulls. What's the probability we get a red ball? Give me a number.
1/6.
How many balls were in the urn?
5.
5. How many of them were red?
3.
3. So, if you reach into the urn, what do you think? You probably don't like 1 out of 6. You're rolling a die in your head, aren't you? I can tell you're rolling a die in your head. So what are you going to do to give me a new answer? Update your answer. Red.
3 out of 5.
3 out of 5. Absolutely. We got 3 choices that are red out of the 5 choices. Again, using the equally likely rule there, that probability is 3 out of 5. And so the probability of getting a white now, a probability of getting a white, give me a probability of getting a white. Probability of give me a white. 2 out of 5. You say, that was easy. Now, I could add to my notation a little bit, but I'm going to start with this, okay? So we went this way. Now we're going to pick our second ball. So we're going to pick our second ball here. And let's see, I'm going to make 2 branches here. Got my 2 branches, because if my first ball was red, now I can look at what my second ball is going to be, and I could still get a red ball, and I could still get a white ball. What's the probability the second ball is going to be red? Well, actually, let's just recognize, of course, the second ball could have been red if I had got a white on the first one too. So I got to be a little more careful about how I state that. I just said, what's the probability the second ball is red? But I really want to say, in the sense of filling in my probability tree, what's the probability that the second ball was red if my first ball was red? What would you say? 2 out of 4. 2 out of 4. Why did you say it was 2 out of 4?
Because we've already chosen one ball, and so that means there are only 3 to 4 balls left to choose, but also it was a red one, so that means there's only 2 red left.
Absolutely, yeah. You picked a red ball the first time, you removed that from the urn, so you've only left 2 red balls in the urn out of the 4 balls left in the urn. So not only is the number of red balls changing, also remember, often people forget that the total number of balls has changed because you've got 1 less ball in the urn. We still have both of the white balls in the urn, so if we pick a red ball on the first pull, the probability of a white ball on the second pull, if the first ball was red, is 2 out of 4. Now, if I had picked a red ball on the first if I've done a red ball on the first pull, I had a 2 out of 4 chance of getting a red ball on the second pull. But if I pulled a white ball on the first pull, what would be my probability of getting a red on the second pull? What would you be? 3 out of 4. 3 out of 4. Okay. So that's kind of cool. That's kind of cool. And what would you have gone with for picking a white on the second if you picked a white on the first? Give me a number there. Somebody give me a number on this side. Yes. 1 out of 4. Okay. So what we notice is that these probabilities for the colors on the second ball are dependent on what we got on the first pull. Okay, so we already have an example here of some sort of conditional dependence here. Okay, and these probabilities are changing based on the information of what happened on the first pull. Well, that's all very interesting. Very interesting. Well, we're going to be coming back to this sheet, so give yourself some space. Give yourself some space. I am not going to answer all those questions right now. I just want to jump ahead to the second example of what happens if we do this with replacement. Okay, so with replacement, I'm going to draw my urn again. Same bucket, same setup, 3 reds, 2 whites. And so now we're going to do 2 balls drawn at random but with replacement. And again, let's think about that idea of replacement means, it means we reach into the bucket, we randomly grab a ball, we pull it out of the urn, we look at it, and we say, ooh la la, it's a red ball or it's a white ball. I look at the thing, I record the color, and I throw it back in the bucket, back in the urn. Okay? So, setting up our probability tree. We go, first ball can either be a red or a white. And I don't think there's any questions that the probability the first ball is red is 3 out of 5. The probability the first ball is white is 2 out of 5. And then we'll go to our second ball. Red, white. Red and white. So what's the probability the second ball is red if the first ball was red? What would you go with?
3 out of 5.
3 out of 5. So are we good with that being 2 out of 5? 2 out of 5? But if the first ball was white, what's the probability the second one is red? What would you say? 3 out of 5. You're giving me the same answers as I got if the first ball was red? That's good. Should give me the same answers. Okay. So let's now look back at the situation. These probabilities, you know, it didn't matter what happened on the first ball as to what the probabilities were on the second ball. But on the first case, it did matter. Well, that is interesting. Okay, well, we need to think about our notation here. I've just gone through and said red, that's just the color of the ball. But if I want to define these as events, I have to be a little careful to set out a better notation. And so, for example, if I said on the first case, let's go to the first case, could I just say, what's the probability a ball is red? Well, no, I can't just go and say, what's the probability a ball drawn from the urn is red, because it matters whether I did it on the first pull or the second pull, and on the second pull it depended what I got on the first pull. So we need to come up with some better notation. And so we're going to denote this notation. I'm going to call this the probability of a red on the first pull. So I'm going to give a subscript as to which pull I am pulling the ball on. So that's the probability of a red on the first pull. Now I want to get the probability of a red on the second pull. But the probability of a red on the second pull, look at those darn probabilities. They're not staying the same. What am I going to do about that? Well, I'm going to recognize that I'm dealing with a conditional probability case, that 2/4 is the probability of getting a red on the second pull, given I got a red on the first pull. And this little sucker here, well, let's kind of go through some other ones here. First of all, I could call this the probability of a white on the first pull. That's nice. Or I could also say that's the probability, oh my goodness, my life flashed before my eyes. Did we have a power failure?
You might have bumped the button. I think is
Oh.
more likely.
Oh, that's more likely. Okay.
Okay, mathematized question. What's the probability he bumped the light switch?
Yeah, that's probably a good one. Okay. Okay. So, I could also say that's the probability of not getting R1, so I could call that R1 complement, right? R1 complement. And actually, I should put this on both screens because it makes it easier for those on that side of this, that side for the time being. We'll come back to the PowerPoint at some point. Okay, so we got that, and I can call this the probability of white on the second given a red on the first, or I could also say that's the probability of not getting a red on the second, given I got a red on the first. And now we also have this one here is the probability of getting a red on the second, given I got a white on the first, which is the same as saying the probability of a red on the second, given I didn't get a red on the first. Because I only had the two choices. And this one is going to be then the probability of a white on the second given a white on the first. And that's the equivalent to saying I didn't get a red on the second given I didn't get a red on the first. Okay, so we've labeled all of our probabilities in the probability tree, and that's all very cool. And now we can go back to addressing some of the questions, such as what is the probability both balls are red? Well, the probability that both balls are red, what I'm going to do there, I'm going to actually explicitly call this intersections. And so what I mean by an intersection is a red on the first and a red on the second is the intersection of the two poles. And I'm going to get these probabilities. So what I want to know is what is the probability of getting a red on the first and a red on the second. And what I'm going to do is say, well, there's a certain probability of getting a red on the first. That was 3/5. And then 2/4 of that time, I'm going to get a red on the second. So I'm going to take the probability of a red on the first times the probability of a red on the second, given I got a red on the first. And so I am going to get 3/5 times 2/4. And that's going to be 6 out of 20. And I could leave it in that, or I could simplify it to 3 out of 10. Okay, so that is one probability. Now, I could go through and fill the rest of those up, but we don't need to do that right now. We can go back to example 2 for a moment. Any questions there so far? Anybody wondering about why I multiplied there? What you're doing, you're saying to yourself, 3/5 of the time I'll get a red on the first, and then 2/4, that's 50% of the time that I get a red on the first, I will also get a red on the second. So you're taking 50% of the original 60%, that's where you get the 30% there. So we can go through and get all of these intersections. We're going to do that, but we want to come back and emphasize something in terms of the second case. this is indeed the probability of getting a red on the first, and that's the probability of getting a white on the first, which is the probability of not getting a red on the first. And this is indeed the probability of getting a red on the second, given I got a red on the first. Oops, I forgot my line there. Red on the second, given that was a red on the first. And this one down here was the probability of getting a red on the second, given I didn't get a red on the first. In other words, I did get a white on the first. But I'm looking at that and going, well, those things are all the same number. 3/5, 3/5, 3/5. It didn't matter whether I got a red on the first. It didn't affect the probability of getting a red on the second. And the probability of a red on the second was the same as getting the probability of a red on the first. So if I want to simplify my notation, I can do that. I can just say, hey, that's just the probability of pulling a red. Okay, it's just the probability of pulling a red. Probability of pulling a red. And similarly, we can go through and work out the situations, but this is just going to be probability of white, 2/5. This is just going to be the probability of a white, which is the probability of not getting a red. Okay, so now doing our intersections. Probability of a red on the first intersected with a red on the second. It's simply, you could say, well, it's just the probability of a red on the first times the probability of a red on the second. But all that is the probability of a red squared equals 3/5 squared equals 9 out of 25. 9 out of 25. Hope I calculated everything right. Okay. Any bugs there? Looking good? Any questions there? Okay. So we got everything we need now to go through and work out a couple of things. Let me go back to my slides for a second for at least one of the screens. I'll switch this one. Can you quickly go through and answer those questions for the, well, that's example 2. There's example 1 without replacement. Same questions, just the 2 different situations, the without replacement and with replacement case. And we're going to set up a mathematized question based on your answers to those questions, and that'll come along in just a couple minutes.
Should we open the poll?
We can open the poll.
Okay.
Exit that. Exit that.
I think if you just scroll down here,
Just scroll down.
it'll take you to the. Yeah, keep going. This is the question I did, and then if you hit this one, hit start. And this is without replacement. Okay. Try pressing it one more time. Okay, there you go. Okay, so it's open on Mathematize now. What's the probability of getting one ball of each color when sampling without replacement? You have to do it. Okay, and I guess we'll. How long do you want to go? Well, you tell me. Yeah.
2 minutes.
Okay, and we're gonna give you until it says 2 minutes. When it says 2 minutes, we're gonna stop. Yeah, you'll have just enough time.
Then we're going to very quickly come along with another question based on the with replacement scenario. Time goes quickly in a class, eh?
Yeah. Yeah. You can probably you could take this one up and then we could assign this one as well. Go try it at home and then come back and then you could start with it on Wednesday.
Let's get those responses in. We are keen to get responses. We are at 2 minutes. A few epsilon seconds to get those last responses in, please.
Okay, so now if you hit reveal and then you go to yeah, so you click on that and it'll give you the option to hit reveal the count. Maybe we'll do that first. Well, you know, you gotta stop at some point.
Yeah.
So that would tell them the right answer. You want to see what they said first.
Yeah, this is
Okay. Then you click here to show everything.
Okay, we have 49% going with 6 out of 20. 41% went with 12 out of 20, and that is the correct answer. And a few went with a couple of the next options, which, yeah, they're wrong. Okay, so, those who got it right recognized the key thing. Those who got it wrong missed the key thing. And let me go back to my dock camera for a second here. Dock camera. Dock camera. What we have to remember, if it's one of each color, is there were 2 routes for getting one of each color. You could have got the red first and then the white, or you could have got the white first and then the red. It is true that this here, and when you work it out, and I'll let you work it out, you should find that this is going to be 6 out of 20, and this is going to be 6 out of 20, and this is going to be 2 out of 20. But one of each color, you've got to add the 6 out of 20 and 6 out of 20 to get your 12 out of 20. Okay, you'll also notice that these 4 intersections add up to 1. One of those pairs have to happen. So, we've, Dr. Nika and I was discussing this. We had another question for you, but we're going to leave that one for the start of next class.
We're going to open it right now. You can put in your guess, and then we'll take it up at the start of next class.
Okay, there's an idea.
So there we
There's
go.
an idea, okay.
We'll do that. We have just enough time. So once you put in your guess, if you can figure it out, then you'll save yourself some time at the beginning of next class. And here, I guess we should display it for people. So same exact question, but now it's the with replacements. Okay, so once you do that, you're feel free to leave. We'll see you guys on Wednesday. We'll be around here for some questions if you have any questions. Don't forget, you have homework due on Friday.